And thanks to all the organizers for having me, and to everybody who's online for attending my talk. This talk is about data-driven learning for non-local models in the context of material response. This research is supported by the LDRD program at Sandia and by the project Films. This is a very brief outline of this talk. I will say something about why non-local or integral operators. I'm assuming that not everybody's familiar with this type of operators, even though they were mentioned today. Then I will introduce the main idea of our approach. And then I will present this approach in action on fast surrogates for molecular dynamics displacements and for wave propagation through heterogeneous materials. These are the people that contributed to this work: Stuart Sealing at Sandia Labs, Albuquerque, Huaishan Yu and UAU at Lehigh University. So a non-local or integral model is a description where the state of a system at a point in space and time depends on a neighborhood of points. So interactions can occur at distance and without contact, as you can see from this picture. Solutions of these models can be irregular. They don't have to be differentiable. They can be discontinuous. They can be pretty nasty solutions. The reason why we're interested in these models is because in some circumstances, they can capture effects in a much better way than PDEs. And in particular, what I'm gonna focus on today is their ability to capture multi-scale behavior. So a non-local model acts as an upscale or homogenized model and is able to capture small scale effects at larger scales. So this is what I'm gonna focus on today. I'm reporting here a very simple expression, but also very general expression of a non-local operator. These operators embed length scales, this delta, and that's why they can catch multi-scale behavior. As you can see, there are no derivatives involved in the formulation, and they depend on this function k, we call it kernel. It is application dependent and determines the regularity properties of the solution. This can be seen as a non-local counterpart of a Laplacian, and as such, it can be used in your favorite equation, elliptic, hyperbolic, whenever non-locality appears. The problem that I'm gonna focus on today is the fact that this kernel cannot be measured and is usually established a priori. And so it's an unknown quantity and it's not easy to decide what to pick. So the question that I'm going to address is, what's the best kernel for a specific application? Or better, can we design a data-driven tool for kernel identification such that what we obtain is physically consistent and well-posed? So the goal is to find this object here, but in a smart way. And we believe that one of the missing ingredients for a robust computational framework for non-local kernel identification is integral theory, is to add some non-local calculus theory to the machine learning technique. So this is our recipe. Of course, especially in this context, I don't need to advertise the combination of machine learning and physical principles or physical laws, but what we want to add in the picture is the non-local calculus for this specific type of operators. And the result is gonna be a new model, new non-local model that is mathematically rigorous, and by this I simply mean solvable or well-posed, physically consistent, but also that generalizes well to settings that are substantially different from the training. I'm gonna assume to be given some high fidelity data, or I'm gonna perform some high fidelity simulations. This is my high fidelity model. It doesn't have to be a non-local model. And actually most of the times it's not a non-local model, because what a non-local model does is to upscale. So I often give the example of subsurface transport. In subsurface transport, where we have a lot of heterogeneities, at the small scales, a PD that captures all those heterogeneities is good enough, is an accurate model. The problem is that we don't have the computational, we cannot afford the computational effort required to solve that equation at the small scale. And so our claim is that even at coarser scales, we do have accurate models, and these are non-local models that are able to capture the small scale behavior at larger scales. And so our goal is going to be to find an optimal non-local model in substitution of this. And we're going to estimate, we're going to find the optimal kernel that well represents the high fidelity model. So we've been working on this for quite some time, and we worked on several methods. And today, I'm mostly going to talk about, the first two. So I'm going to start from this non-local operator regression, and this was introduced more or less a year ago in a work that co-authored by two of the presenters yesterday, Nat Trask and Mami Kangulian. But then we extended this technique, which was firstly developed for 1D static problems. I'm going to describe this technique in 3 simple steps. I think it makes it easier. So just keep in mind that the goal is for this simple operator to determine the kernel function, this function gamma. So we collect measurements. These can be, as I said, high fidelity simulations, and we have pairs of solution and forcing terms. Then we pick a surrogate for the kernel. In this case, the surrogate is a combination of polynomials. And in this paper, in our first paper, we picked Bernstein polynomials. This doesn't have to be a combination of Bernstein polynomials. It can be a neural network. So, and it really depends on the application that you have and on the behavior that you want to capture, how simple you want this surrogate or complex you want this surrogate to be. Then the third step is to minimize the residual of the non-local equation. So impose weakly by optimization that the physical laws are satisfied. And the constraints are solvability constraints, meaning well-posedness conditions that come from the non-local theory. And the outcome, of course, are the coefficients of this combination that uniquely identify the kernel. Now, note that everybody is formulated at the continuous level, and what we're gonna get as an outcome is a continuous function. And so this resembles what was presented in the very first talk today about operator learning. And this is exactly what we're doing here. We're working at the continuous level, and this is why then you can use this optimal kernel at any resolution. An important feature of this first work was the fact that the embedding solvability constraints in this optimization problem. It is very easy to impose a solvability constraint, which is to ask that the kernel is positive, but this limits big time the descriptive power of this operator. And so we were able to embed some solvability constraints that allowed the kernel to be sign changing. Now, I'm going to show you in a simple example. This is elasticity. I'm going to show you how we used it. So we are in the context of materials with heterogeneities. And what we have here is a bar or a 2D body with heterogeneous microstructure. And the operators that we consider are the same. So our high fidelity model is the classical elasticity equation that for data generation, we're gonna solve by the finite element method. And the candidate non-local model is the one that I introduced at the beginning. And in this case, we have the additional second time derivative. And we apply the operator regression, but we add some physics constraints here. And we realized that when using operator regression, depending on the application that we have, adding everything we know about the physics of the system really makes the difference. And I'm going to show you how. So in this specific case, our physics constraint is to ask that the total energy of the system that comes from the optimal kernel that we find matches the one that we know from mechanics of the whole system. So what we have here is the acceleration, is the predicted acceleration. We have on this column, on the left column here, the reconstruction without energy constraint and the one with energy constraint. And this is the kernel, the optimal kernel used in settings that are different from the training ones. So we're changing loading conditions to see if the kernel generalizes well to settings that are different from training. And as you can see, the first line is the X direction, the second line is the Y direction, and we're picking a point in the body and following the acceleration in time. And when we apply the energy constraint, in both directions, we have a pretty good match of the acceleration. Now, I'm gonna switch applications and I'm gonna talk about the use of this technique in a molecular dynamics setting. Just to give you some background, what we want to do is to use non-local models to bridge the molecular scale and the continuum scale. So what we're claiming is that we can describe molecular dynamics displacement by using a non-local model. And the ultimate goal is material design and testing, because it's well known that molecular dynamics is becoming a very important tool for material design. I have several slides where I describe how one can go from molecular dynamics displacement to a continuous integral equation, but I'm gonna skip that, so you're gonna have to believe me on that. But once again, even in this context, it's not clear how to pick the kernel. So once we have decided that we want an integral model to describe at the continuous level molecular dynamics displacement, there's still the question of how to pick the kernel. And so we're going to apply the technique that I just described. How do we generate the data? So since we want to test generalization properties of the algorithm, we're going to pick two very different training set and validation set. Here, these are molecular dynamics displacement, very oscillatory. We have 70 samples generated with this oscillatory forcing terms where we change the frequency and we keep the temperature constant. This is the displacement. This is the velocity associated with those displacements. And the reason why I'm reporting the velocity is because there is to highlight the presence of thermal noise, which happens as we increase the temperature. So we considered both zero temperature where there's no thermal noise and then increase the temperature to see how the algorithm behaves as the thermal noise increases. Instead, this is a validation sample. So it's a completely different forcing term. And this is because we want to see how the algorithm behaves in first determining material properties of this specific material, and I'm going to say more about it, but also how the algorithm behaves where we change the loading setting, when we change the temperature, when we change the domain. All these experiments are done with a single layered graphene. So this is the material we're using simply because there is an ongoing project at Sandia that is using graphene. There are some parameters that need to be tuned. This is a very new project, so some of the results that you're going to see were generated a couple of weeks ago. So it's really a work in progress. And so we don't have an optimal way for choosing the number of basis functions and the delta, so the extent of the non-locality. So what we're doing for now is just to perform some simulations and see what's a good combination of these parameters to prevent underfitting and overfitting, and we do it by looking at the loss over the training set and the loss over the validation set and the relative error in the displacement. And so we pick some optimal parameters. We do simulations, we do testing both at zero temperature and higher temperature, 300 Kelvin. And we were happy to see that we are able to recover a very specific feature of graphene, which is a negative Poisson ratio, which can also be found in the literature. So we were happy to see some consistency with experimental data. This is just to report the shape of the kernel at 0 Kelvin, and this is the comparison between 0 Kelvin and 300 Kelvin. And some material properties do change, but overall, they're pretty robust with respect to the thermal noise. We also did some tests in terms of generalization with respect to the domain. So just to recall, this was a type of training sample that was used to train the model. This is where we validated the model. And now we want to completely change the setting, consider a different domain, which we renamed coronavirus domain. And we wanted to test the optimal kernel generated here on this new domain with also a different forcing term. And this is the most recent result that we have. And we have a prediction error in the displacement of the 10%, which we believe is already a good result. But of course, there's a lot more to do in this direction. We're also investigating mesh independence. So independence of the accuracy of the prediction to the resolution, which we do have, but we need to be careful because some of the well-posedness constraints that we're prescribing are discrete, and this can affect the well-posedness as you change the resolution. Anyway, I don't have time to talk about this, and so I'm gonna switch to the last application that I wanted to talk about, which is where the approach is a little different, and I would say is more traditional than the one that the operator regression that I just talked about. And this is the nonlocal counterpart of PD constrained optimization, basically. And so we're gonna change slightly the formulation. This is what we want to simulate. So once again, we have a heterogeneous material. In this case, we're considering a periodic microstructure, and we want to reproduce wave propagation, but we want to do it in a way where we don't have to solve explicitly for these interfaces. The nonlocal model acting on a scale that is larger than the microscale is gonna capture the microscale effect. Still, we don't know how to pick the kernel, and so we will let optimization find that out. The kernel is still described by a linear combination of Bernstein polynomials. The unknowns then are these coefficients. They're scaled by the nonlocal interaction radius simply because this is always used in nonlocal models to make sure that when delta goes to 0, we recover classical equation. So this equation goes to the classical wave equation as delta goes to 0 or as the non-locality vanishes. So here the loss function is different. So we're simply minimizing the difference between displacement, the predicted displacement and the measurement, the high fidelity displacement that we have. And we have a simple Tikhonov-like regularization of the coefficients. And the constraints are the non-local equations. Now, the reason why we didn't use the minimization of the residual is because we were not getting accurate results. So we had to match the displacement to get accurate results. On top of it, we realized that to accurately predict wave propagation, we had to add new physics constraints. So just prescribing that the displacement was following the wave equation was not enough. So what we added was that the group wave velocity of the nonlocal model could match the exact group wave velocity. And this physics constraint basically translates into prescribing the value of the fourth and second moment of the kernel. So these are very easy constraints, and they could be enforced in a strong way. And from these two constraints, we simply derived the two of the coefficients and expressed all other coefficients in terms of these ones. So it's strongly embedded. So I'm going to show you how matching the group velocity actually makes the difference. We train on plane waves. These are very simple. This is the domain. These are very simple waves, just a sinusoidal boundary condition for the velocity at one side. And we use different frequencies. This is the optimal kernel. It is allowed to be negative. The problem is still well posed, simply because the time dependence makes it well posed. And this is the group velocity. And the light blue curve is the exact, let's say, group velocity obtained with high fidelity, with an exact solver for the velocity. The black line is the group velocity that we obtain from our learning. We compared it with some state-of-the-art kernel. This is a constant kernel derived optimally, analytically, but it's Even though it matches the group velocity for low frequencies, it does a very bad job in catching what's called the band stop or band gap. And catching a band gap is very important because going this profile means that when we go beyond this little omega, the waves stop propagating. And we will see this in our experiments. So based on the kernel learned on plane waves, we use as a validation set a wave packet. Now, a wave packet, and we use it on a different domain. So we change the size of the domain and we change the velocity boundary condition and we test it at different frequencies. So this is one of the frequencies where both our optimal kernel and the state of the art behave pretty well. And in fact, there is a good matching compared to exact velocity. This is a frequency very, very close to the band gap. And we do a decent job, especially compared to the state of the art. And when the frequency is beyond the band gap, we see that the wave stops propagating as expected. This is the state of the art kernel. Since there is a good matching here, this kernel also does a good job on low frequencies at 2, which is what we have here. But close to the band gap and beyond the band gap, we have this kernel completely misses the fact that the wave is not propagating. The last example that I'm going to show is, again, a different setting from the training one. And what we're doing here is to simulate a projectile impacting this heterogeneous bar, a bar with periodic microstructure once again. And basically the impact generates a boundary velocity here. The first column is our optimal kernel that does a good job both at small times and at the short times and long times, while the state-of-the-art kernel misses the initial times. And this is mostly because it was developed to match long times. So it cannot, a constant kernel cannot do both. What we're, a small short summary. With both these techniques, and it's mostly the formulation of a continuous optimization problem to learn a continuous form of a kernel, delivers a new nonlocal model that at large scale or at scales that are larger than the macro scale and molecular scale embeds the material properties and allows to capture globally small scale effects. We saw from these experiments that with these optimal kernels, we can model scenarios that are substantially different from the ones used during training. And this applies to noise and applies to forcing terms, but it also applies to the size and shape of the domain. What we're working on right now is transfer learning across discretization types, because at the end of the day, during learning, you have to discretize. And we're wondering what happens when you discretize using mesh-free, which is what we're doing right now, or finite elements, for example. And in the molecular dynamics setting, what we're going to introduce is damage, and this will require a lot of modeling work before getting here. But I'm going to stop here, and I'm happy to take any questions.
Thank you. We have 2 questions from Carlos. First question is about your MD simulation. So is it possible to model this using a mesoscale, applying something like phase field to work in a continuous setting?
Yeah, I mean, there are other models. No, local models are not the only choice. I think I have some, let me show you how we get to the continuous model. We just simply start from a set of particles which have forces between them. And we simply apply Newton's second law. And then from the particles, we introduce some smoothing functions. And this is how we go to the continuous setting. And we redefine all the quantities based on these smoothing functions. So we have continuous quantities, and the same applies to the displacement. Now, once you differentiate in time and you apply to the displacement, what you're gonna get when you take the limit is an integral equation. And this is why we claim, this supports the fact that smoothed molecular dynamics displacement fall on local law. But there are other coarse-grained models of molecular dynamics in the literature for sure.
Yeah, I guess the phase field model is more like, the multi-scale model, like in subsurface rock and the inclusions, material and fracture and other kind of things. But I think homogenization of this kind of the model can be applicable.
Yeah, no, that there are certainly different options. We like nonlocal models because of their ability to catch well these type of interactions, but it's not the only choice.
Okay. Second question was from the same Carlos, and about the wave propagations.
Sure.
Are there other conditions such as energy entropy that could be imposed in addition to the wave equation?
Anything you know about the system, in my opinion, can be included in the equation. We stopped at the wave velocity, at the wave group velocity. If there are additional conditions that would make this problem even more robust, sure. I think any physical knowledge can be included and is not gonna ruin. Actually, it's gonna improve the generalization properties. That's what we noticed. We didn't need any well-posedness constraints here, for example, because the problem was well-posed by itself.
Okay, thank you so much. And
thank you.
So any other questions from audience? Actually, quick question about your transfer learning.
Sure.
So are there any kind of fine tuning, like updating kernel parameters or other things? Just one geo-shot inference to your different application, like coronavirus application. So I guess some sort of boundary condition and other things can applicable. Not really.
I think the deal here is that so when you learn a surrogate for the solution, this surrogate is really affected by boundary conditions or things that you apply directly to the solution. In this case, since we're learning, it doesn't matter if, and by the way, all our learning, our training data have the same type of boundary condition. But still, since we're learning an operator rather than a surrogate for the solution, you can take this and place it anywhere because what you're learning is something that describes the material and not the solution itself. So I think what makes the difference is really the continuous formulation and the fact that you're learning an operator rather than a surrogate for the solution.
Okay, great. And thank you for the great talk.
So, thanks a lot. Thanks for having me.